and welcome to ChiPy's main meeting for April 14th, 2022. Before we get into anything too deep, we do have a code of conduct available at this URL that'll tell you what's expected of you as participants and what you can expect from us as your organizers and presenters. I'd like to take a quick moment to thank our sponsors. These folk have helped a lot cover the expenses of streaming all this stuff to you live, and occasionally giving in-person meetings as well. So you might be asking, what is ChiPy if this is your first time? This is a Python community. We've been around since 2003 holding meetings and various other events. So this is the names of our board members. These are the folk you can go to at any time if you've got any concerns about presenting or holding a meeting. And we've got various other initiatives other than this particular meeting, which we hold once a month. Not all of these things happen every month, but I know the AlgoSig has been particularly has also been happening regularly. So upcoming, as I said, the Algorithm SIG is on Thursday, May 5th, and our next main meeting will possibly be May 12th. In addition, I'd like to remind you all, PyCon US is coming up. It's in Salt Lake City this year, and should be quite an interesting time. There's often a lot of good presentations to be found, and a lot of good knowledge to be had and shared with various other active members of the Python community. So where you can find us, we have a very active Slack. Domains available here. Our Twitter is also available, and you can always find us at chipy.org. So tonight's schedule, we're going to have a presentation by Adrian on Espresso and another presentation by Craig on Introduction to Geospatial Data with Python. Both speakers will be doing a Q&A, so you can type your questions into the chat over there on the right-hand side of YouTube, and we'll answer them as we can. All right, with that, I think I'll turn it over to our first speaker, Adrian.
Hi, folks. Pleasure to be here, and thank you to the organizers. I moved to Chicago not that long ago, and it's actually been great to find a community to talk with and learn with, especially now when so many things are remote. This meeting was in person, but I'm hoping that future ones will be. So the topic I'm presenting on tonight is Espresso, which is a Python web framework that I've been working on, and really more than that, it's, for me at least, it's been kind of a proving ground of ideas and just exploration on what we can do with a lot of this new ecosystem that we've unlocked in the last couple of years with the ASGI standard and just async Python in general, as well as typing, and even more recently PEP 593, which supports annotating types. So I'll be showing how that all plays into creating a modular and composable ecosystem for a web framework. And let me go ahead and share my screen here. Yes, I accept sharing my screen. This is my first time sharing from Chrome, so I'm probably going to have to quit and restart. So sorry, folks. I'll be back in one. All right, sorry about that. I'm back. Obviously, StreamYard only supported Chrome, and I had never shared my screen on Chrome before, but now I can share my screen. Yeah, so Espresso is inspired by Fast API. It's built on top of pretty much the same stack, Starlet and Pydantic. Starlet provides all of the HTTP stuff, essentially is a layer between the ASGI server and the user code, which takes care of like defining the request model and all that kind of stuff. And Pydantic is a data serialization and validation library, which allows you to declare your JSON schema and that sort of thing. Just like Fast API, it uses type annotations and it generates open API specs from your code. And it is fundamentally centered around a dependency injection system, which is how you get query parameters and path parameters and headers and all that sort of good stuff. Why did I create this? Well, in great part because I really love Fast API when I found it. But I found some parts of the design that I thought could be interesting to change. So this project was kind of embarking on like, what could this look like? Where could we take this? And I found that the central issue I wanted to change was decoupling the dependency injection system from the request response cycle. And in doing that, it enabled a lot of different moving pieces to kind of fall together. So the first step I took at this was to build a standalone dependency injection system. And I wanted to design it in a way in which it, could be incorporated into Fast API if that came down the road, or not, where it could also stand alone as its own thing. So I called this thing DI, which just stands for dependency injection. And you don't really need to exactly know what dependency injection is to see how it works. The gist of it is, you have some sort of object that you want to create. In this case, we have a B, which depends on A, and you see that because A has a field or constructor parameter that accepts an instance of A, and so we can say, well, please give me a B, and the dependency injection system will figure out that you need to construct an A and give it to B to make it work. That's just the basics of what the dependency injection system is doing. Yeah, so there's a lot of boilerplate here, but the point is that this isn't meant necessarily to be used directly. This is actually what both Espresso and Fast API are doing behind the scenes. The only difference is we're trying to make it, I'm trying to make it explicit here, so that we can build things on top of it and compose it instead of it being kind of buried within the web framework. So what to do after that? I submitted this as a proof of concept to Fast API, but at first the maintenance team didn't show any interest. So I decided, let's try and build something new. Let's try and keep experimenting. So I built this web framework called Espresso, and I built it just like Fast API is built on top of Starlet plus Pydantic, and adding in a third component, which is a dependency injection system. So I have an example here of what an Espresso app looks like, but fundamentally, it's very much the same as Fast API. It's a Python package. You can pip install it, and using it looks a lot like it would to use Fast API. You declare your schema. If you're doing a JSON schema, you declare your schema. You can declare path parameters that you accept. Like in this case, we require a path parameter called item ID, as well as a query parameter called name. And because there's no default value and it's not optional, it is required. So if you send a request without it, you'll get an error. So far, it's very much the same as Fast API. Now, one thing I'll note that's different, which is that we're not using default values. Like there's no equals path. It's using this from path. And I'll unpack that in a bit, but that's using PEP 593. So essentially, this is just, as far as the type system is concerned, this is just an integer. And from path is just metadata that's telling the framework where to grab that integer from. Yeah, so you just declare your parameters with type annotations, and then you build your app using this constructor style, which is slightly different than the decorator style, but it's actually the preferred style in Starlet as of recent versions. So Fast API is lagging a little bit behind that, but since I was building from scratch, I went with the preferred method in Starlet. Request bodies are just like Fast API. Also using Pydantic, you declare your schema, And then you say, I want this to come from JSON. But unlike Fast API, you can also use the schema for other things. Like in this case, I'm also saying the return type is the same thing. So that makes for a really small function handlers, just accepting JSON and returning JSON, and I don't really have to do anything else. But all this will generate the Open API and will generate a validation for it. Multi-part requests are actually somewhere where I diverge a lot from Fast API, and it's a lot more similar to how you do it maybe in Django, in the sense that you declare a model for your form and you declare each field for it. And within those fields, you say, I want this to be extracted from a field, and I want JSON to be extracted from it, and I actually want it to be a list of images, or I want this to be extracted from a field and it's actually a list of files. And I want them as bytes instead of like upload files or a raw stream of bytes. And then you tell your function, your handler, that you want to extract that entire object from multi-part. And so then it's going to go and it's going to check if it's a multi-part request. If it is, it's going to extract each one of the fields. And for each one of those fields, it's then going to go and extract, JSON or files or whatever you told it to do. There's also, you can use the raw dependency injection system, which is actually a lot more powerful than what you have available in Fast API. For like in this example, I'm just declaring some database class, and then I'm saying that I'm creating a dependency on it, but I can declare with an application scope, and that essentially makes it a sort of singleton. Really, it's just scoped to the application lifetime. But I don't have to do any sort of like LRU cache sort of thing to kind of get around the fact that it's called every time. I can tell the dependency injection system, you just build this once and keep it around. And then lifespans are also using the current Starlet convention of just using an async context manager as opposed to using startup and shutdown events. So Espresso only supports the async context manager approach, which has a lot of advantages and is the way that Starlet is doing things moving forward. And then you just build this all into an application. So the idea is you kind of compose it all in the end into one application. You take your routes, you take your lifespans, and you just put it all together, and that's what makes an application. And with that, I can show a live demo of some of the cool things that you can do with this. So like I said, it's very much just like Fast API. You're creating an application, you can serve it with Unicorn. We're using the exact same middleware, but there are some differences. So one really cool feature that having this more powerful dependency injection system enabled is running dependencies concurrently. So in Fast API, if you're like validating a JWT token at the same time that you're reaching out to the database to see if the user exists in the database, those two things have to happen sequentially, one after the other, even if it's all async. And so in theory, it could all run at the same time. There's just no way to tell the framework to do that. You end up having to run it separately. Similarly, there's also no way to make a synchronous dependency like this one and decide if you want to run in a thread or not. If you make a sync dependency, automatically gets run in a thread, which means that if you're doing something trivial that requires no IO, you end up running that in a thread, which is really counterproductive for performance. So like in this case, we have two dependencies. They're just trivial placeholders that call sleep. One is an async dependency, which calls async IO.sleep, and the other one's a sync dependency, which calls time.sleep. Our endpoint is going to depend on both of them. But I'll point out that the sync dependency, I'm using sync to thread equals true, and I could easily make this false, and then it would block the entire event loop. But you as a developer get the choice of what you want to do with that. Only you can really know the performance characteristics of the code you're writing. And then in the route itself, I have an endpoint. And this endpoint, like I said, just depends on these two dependencies. It's really doing nothing other than depending on them. And aside from just returning to you how long it slept for total between both dependencies. And here's the cool stuff. I have this parameter here, and I can just flip this from true or false And this alone is going to determine whether the dependencies are executed concurrently or not. And so if I set this to false, and I run my app, let's export that. So if I run my app with that as false, and I call my endpoint, which is aptly named sleep, and I call it with, I don't know, 5 seconds. This is going to take a total of 10 seconds, because again, it's just running things sequentially. And so yeah, you'll see it took 10.04 seconds, and it slept for a total of 10 seconds. If I can just come here and flip this to true, and now Espresso is going to optimize concurrent execution of my dependencies. And that means it's not just running 2 at the same time. It's using the algorithm in GraphLib, which allows you to do online, essentially allocation or topological sorting of dependencies. And so as soon as one is done, it'll start the next one. So if I do this again, it'll still sleep for 10 seconds total, but you'll see that it only took 5 seconds to execute. And that's because it's doing both sleeps at the same time. And not only that, it's doing the synchronous sleep in a thread. So there's no block in the event loop, and I can do both things at exactly the same time. The Open API, like I said, it generates Open API just like Fast API. It has slightly more advanced support for query parameter parsing and that sort of thing. So I can, for example, if I want to add a query parameter here, I could say param, and I'll make it like from query. I'll make it a list of, I don't know, integers or whatever. And that'll work just like in Fast API. If I refresh this now, you'll see that this takes a query parameter, and it's a list, so I can add multiple of them. That's all fine and dandy. Now where it gets really nice is if you're trying to port an existing API, it may, for example, it may accept query parameters as 1, 2, 3, or a equals 1 and a equals 2 and a equals 3, and that's all defined by the Open API spec. And here you can actually customize that. So from query is actually just a thin wrapper around using annotated, which is PEP 593, with some metadata. And so you can actually create that metadata. There's a default, but you can create whatever you want. So here, instead of query, I'm just going to import query param, and I'm going to say this is a query param. And by default, I have exploit equals true, so I can just make exploit equals false, and it'll work just as well. So here, if I tell Swagger to build this request with the existing Open API I have, you'll see it encoded the parameters as where do I have it? Param equals 1 and param equals 1. But if I come here and I change this to exploit equals false, and I rerun this, I'm gonna get the same Swagger docs, but if I do 1 and 1, and I run this, and it's gonna sleep, you'll see it encoded as param equals 1, 1, because all that is defined by the Open API spec, and you have a lot of flexibility in how you encode the parameters. Other than that, there's not that many differences with Fast API. It's mainly been an interesting exploration of what's possible. I found PEP 593, the annotations, to be really promising for the entire ecosystem. I think it allows a lot more composability than anything we had before, because you can have more than one piece of metadata. So, for example, let's say I also want to apply a regex to this field. In Fast API, this piece of metadata that exists, it exists as a default value, but it also exists. It's a class that inherits from Pydantic's field class. So what happens if you want to have some sort of extracted thing that's not through Pydantic? Like, what if you want message pack or something? The answer is you kind of can't do it because there's a lot of inheritance going on and mix-ins, and it's hard to get away from that. But here we can just say field, and yep, that's what I want. I want Pydantic field, and I want this to be, I don't know, can I do reg set parameter? So I don't know, I can say this has to have foo in it. And so if I run this again, on field run, well, I mean, it is a live demo. Or set by non-enforced. Okay, fair enough. I think I can do like GE2. And obviously this is not something that's ready for anyone's production use. I think it's interesting to explore. I think it's interesting to think about these ideas, but I don't think it's ready for anyone's use. Okay, so you'll see it pick that up in the Open API, and it's saying, yes, it has to be a minimum of 2. But these two things are completely separate. I get to declare the serialization and deserialization that the web framework is going to use completely separate from the Pydantic model. And so I can like mix and match those things without being forced to, have like a single inheritance chain. I think that's a really, really cool thing about PET 593 that I found as I was working on this project. Yeah, that's, I mean, pretty much it for the presentation. I'm open to questions. Oop, now we have this going on. How do I get away from this? I don't know if there were any questions in the chat. Let me stop sharing. But yeah, that's been the project. I think at least I've learned a lot from it, and I think it's been great to cross-pollinate some ideas. Some things have been upstreamed into Starlet. I've talked with Sebastian, the author of Fast API, and we're working on getting some of the ideas into Fast API, even if it's not directly as code. Yeah, I mean, it's been a fun project. I think, these sort of experimental things should happen more.
I'd agree, Adrian. Thanks for presenting. All right, so I think we have a 10-minute break between presentations, if memory serves, Aaron.
I think we can get by with maybe like 2 or 3. Just give people a
2 or
break
3.
and come back.
Fair
Thanks.
enough. All right, back in 3, y'all. All right, and welcome back to ChiPy Stream. Next up, we have a presentation from Craig Barnes on working with geospatial data in Python.
All right. Well, thank you. I assume you can see my screen, so I'm going to go into the presentation. So let me introduce myself really quick. So although it says I currently, let me start this. Sorry about that. Beginning. Okay. Yeah. So well, it says I currently work for the University of Chicago, which is true. I used to work for a company that's based in Chicago called Here, and they make digital maps, and they've done it for about 30 years. So spent a lot of time working on geospatial data, primarily with Python. And so just give what I want to do is give a brief introduction to what is geospatial data and how can you use Python to find some interesting ideas or display data or process data and find a giant wealth of information that's out there that you can actually take advantage of. So really, geospatial data combines a couple of different things, mostly location information. And so, most of everyone now knows about GPS traces or knows that you can find locations on your phone or use your phone to show people where you are. And that uses, latitude, longitude. And that's usually how everything in the world is mapped to. Mostly outdoors with GPS, indoors it gets a little stranger. We can always talk about that. There's attribute information associated with this data. So, a point on its own is probably not that important, but a point on its own that tells you that, by the way, this is the outline of a building, this is the height of the building, this is the year the building was made, this is the number of offices in the building, etc. I can do that. And then the other one, which of course has shown up more recently, I'd say in the past 10, 15 years, is temporal information. And that's sort of what we call GPS traces or events that occur at certain locations and then disappear. And all these are used to create maps and then also extend into something we call location intelligence. Your common geospatial data is typically points, lines, polygons, and then multiples of above. And I have some examples here. You're all familiar with like the marker for where your restaurant or any place of business is on a map. Of course, street networks or streets are usually considered it to be lines. And then polygons usually represent building outlines, what they call cartography features, which are like lakes and parks and oceans and everything else. So you'll find those all over the place, but there's also a bunch of other different things you can find as well, or actually use. You can use meshes. So you want, your buildings, instead of being flat, can be actually models. 3D objects, which can be arbitrary things. Usually what you'll find in maps is like what they call landmark buildings, which are more like super sort of detailed, rendered and textured objects that look more like the real world, but you don't want to do it for everything because it takes forever to render. There's elevation data, so you can do like hills, valleys, anything you want to do there, ocean depths, things like that. And then you find some more rare stuff like LiDAR, which is what a lot of companies use to map cities and county governments use it to map elevation data and things like that. So you can start getting height and topology on there. You can get GPS traces, as I said before, which is, traces of people's location over time or cars over time. There's car data, which is interesting. Your car actually pretty much nowadays, especially since most cars are more electronics and mechanical, will record your information, and, they can use it on their own, or the OEMs will use it to learn things about driving habits. Insurance companies use it to give you discounts on your insurance if you're a good driver. There's something called HD maps, which is high definition maps, which are used for autonomous driving, that are accurate, more accurate than like from a meter, which is what usually maps are, half a meter. We're talking about down to centimeters or millimeters. And then of course there's images, and that satellite imagery are what they call, are other images that are usually collected from planes. And then the other ones that are important about geospatial data is it has attributes and temporal information, as I said before. And, location by itself, not necessarily the most useful thing, but you bind it with names, measurements, other metadata. In the cases of places of business, the business hours, its telephone number, its address, that's pretty important. For temporal data, you want to do things like GPS traces, the concept of events, and events can be anything from like parade, meetings, to, traffic incidents on the road, which can, of course, cause traffic. So all this is out there, and all of it is used to do things. And then there's a bunch of other things you need to consider when you actually talk about geospatial data, and it gets, I mean, just starts kind of exploding on you. Different coordinate systems, so there's degrees, latitude, longitude, there's Cartesian, XY, there's all the exotic ones. I call it exotic because you get weird altitudes, you get digital elevations can be kind of strange. When you talk about trying to map things indoors, that also gets weird because you need a coordinate reference system, and it's kind of hard to figure out where one is. You can't use GPS indoors for a ton of reasons, but mostly it just doesn't work. The other thing is that the Earth is round, which can be inconvenient. It's great for us, but it can be processing the data, and you have to do things like project it from one coordinate system to the other, from a globe to square. And when you do that, you get distortions, all sorts of things like that. You have file types. So you have like shape files, which we'll go into, GeoJSON, which is a JSON representation of it. Things called map, the vector tiles. Mapbox is a company that makes something called a Mapbox vector tile. And there's digital elevation models, which can be all sorts of different formats, from really high resolution TIFF imagery to just large binary files. There's also the idea of ordering all this information, so we call spatial decomposition, or which lets you break the world down into more manageable chunks. And of course, one thing about location data is it's always messy. I mean, you can have the most beautiful data in the world, and there's always something that's going to be wrong with it. It can be extremely unorganized, and it can be also huge world scale, for sure. And then we're talking about building a map. So maps are built by layering various different locations. Kind of interesting, because what happens is you build a map and you render everything on top of each other, and all looks like it knows, it's all spatially aware. But the problem is that all that data is kind of disconnected. And so you can do some geospatial analysis with this data, but the problem is you need to do something called conflation, which is actually combine these in a way that actually makes sense. And that becomes really, really important to do more complex insights you want to do with data that you want to do. However, the nice thing is Python is one of the most used languages to do geospatial processing. I've used it in my previous position for about 7 years, processing all sorts of doing spatial analysis, doing coordinate conversion, creating 3D geometries, turning 3D geometries into 2D geometries. We even had projects where we were running like huge Python processing pipelines that would do all the world data in about 10 hours and produce like a new database every 10 hours. All orchestrated using cloud services with AWS, everything written in Python. Nice thing about Python, and reason why it becomes super, super useful, is that there's actually a fair number of really good tools for it. And it has almost, you can call an ecosystem, and we can talk about that a little bit. So importantly enough, you need to process geometry. And so you have Shapely. And so Shapely lets you do some manipulation of geometric objects in the Cartesian plane. And the reason why that's asterisk there is it's important to understand. And I'll explain why. And so you can do things like you can turn lines and expand them. You can blend things together. You can take polygons and unions of them. It's extremely useful. It's one of the go-to packages you want to be able to use, and fairly easy to install. Just pip install Shapely. Super useful. Relatively slow. It's not known to be fast. It actually, most of it is written in Python. Which is fine, but it can be problematic when you're trying to process, hundreds of millions of objects. There is a new version that eventually will come out, and they're actually changing its back end to something that's more sort of a compiled, basically written in C++, so relatively fast. And some of the performance metrics I've seen on this library is it's like orders of magnitude faster than the current version of Shapely, which I think will help adopt Python even more. There's also other more complex ones. So there's Pandas, which is used a lot in the data science community. A great package for doing things, for especially columnar data or CSV files, or any type of data you really want to deal with. There's Geopandas, which is an open source project to add support for all this geographic data into Pandas. It can be kind of a pain to install. Usually use Anaconda to install it because it brings in all the other dependencies, and there's a lot of dependencies. Unfortunately, some of these libraries are dependent on a library called GDAL, and GDAL is useful, except the fact that it's written in C++ as a dynamic library, and on various different environments, it can just become a pain to try to get that working correctly in the way you want to. Windows being the most painful, OS X and Linux being less sort of painful. But you can do all sorts of, building your notebooks, and you can do all sorts of analysis on like population distribution and various different multiple plots of doing things. So you can kind of do quite a lot with it. And there's a ton of other packages. So there's Fiona, which uses GDAL, which is what I talked about, which is GDAL itself is Python bindings to a very, very complex C++ library that's itself based on something called the Java topology suite, which was written in Java. GDAL is a C++ version of it, and then there's Python bindings to it. And actually, I'd say that my experience has been that using GDAL in C++ is actually much more difficult than using it in Python. There's RTree, which lets you do some spatial indexing, so you can actually build things with that. And actually start doing these conflation I'll talk about. And then the demo, I'll explain why and how we can build one of these things up. There's something called shapefiles, which is a relatively, actually a pretty old file format, but pretty reliable. You'll find a lot of data in shapefiles. You'll find a lot of data in GeoJSON. The problem is that when you start scaling it up, shapefiles actually are more efficient in terms of file size, and doesn't do really compression, but the binary representation of these objects is actually a lot more compact than the textual representation that you get in GeoJSON. So you can actually process these files usually much quicker. And so there's PyShape, which has been around for a really long time, to let you sort of read these and write these back out. Pretty useful. Something called PyProj. And so one of the things about the world, as I said, it's round. And so you need to actually do a lot of transformations from one coordinate system to the other, because various different data may or may not come in, degrees. It may come in something else, which is usually meter based, but it can be meter based. It's like where it's based on the state of Illinois or, the country of Ireland. And so therefore you need to actually project these back and forth, because you may have data that's in degrees, you may have a GPS trace, and you need to connect those. So you can actually do a lot of projection back and forth using PyProject relatively efficiently. And then there's another one that actually does some coordinate transformation, which I'll demo today, which is called PyMap 3D. Provides, a basic set of coordinate transformations, but it actually is pretty useful for doing some geospatial processing and trying to get insights onto data. And then the other one that you can use, which is great if you have a lot of data and you just want to sort of browse it and look at it and build your own set of maps, is QGIS. There's a company out there called Esri that makes a really nice professional set of geospatial applications that let you do this. QGIS is like the open source version of that. It's pretty powerful. You can view and edit geospatial data. You can actually go in if you have the data. If it's vector form, if it's a raster, you can't really do much with it, just an image. But you can edit spatial data, you can reproject it, you can do some basic analysis. There's a huge number of plugins. They're all written in Python. They all have, actually fairly straightforward, easy to write these plugins. And then also, if you really want to, you can open up a console and then use the interface plus your own command lines to actually do some additional processing and actually be able to do a lot more than just running it via the interface. And then, whenever you want to look at geospatial data, you want to know where you can get it from. And so there's a large number of places to get the data from. And so there are plenty of them, but they vary in quality. There's one called OpenStreetMaps, OSM. They've been around for a really long time. They do community edits. The nice thing about OSM is that in the United States and in Europe, and it's really accurate. There's a large active community that actually gives you lots and lots of contributions. Microsoft donates lots of money to them to help keep them running. They're the de facto standards for doing data, and you can get data from almost anywhere in the world. Build your own maps, start your own. You can do whatever you want to with them. Large number of businesses are actually like Mapbox and CartoDB and a few others are based on the data that comes in from OpenStreetMaps. One thing I'll mention about collecting geospatial data is that someone has to do it. It's can be very expensive and very time consuming. OSM has a very active community that lets you, does a lot of contributions. And then there's other ones. There's state and federal, like U.S. Geological Survey will give you elevation maps and a bunch of data. A lot of states are really interested in understanding what their geometry and topology is for the state. So you can find anything from, just, maps of roads or back roads in certain areas to like what they call LiDAR data, which would be really separate points, but produces a mesh that lets you look at topology, lets you understand, like where floodplains are, where rivers could be, where rivers are shifted. And, it's kind of a hodgepodge. There's no real central place to do it, but, you can go to various different states and find things. In Europe, the European Union has a more standardized version of where these come from. So there's a lot of sources for that. And of course, there's commercial. You can go Mapbox, which if you're an enthusiast and want to play around with that, it's web. It's sort of JavaScript and web based, but it has data you can use, some analytics you can use. Something called Studio, which lets you similar to what I just showed, the QGIS, but sort of on the web based. There's Google has some data. There's CartoDB, and then there's other platforms like Uber, who has some visualization platforms and some data you can get. And then there's city data. So a lot of cities in the United States and cities in Europe and other well-connected, in Asia have a fairly large collection of city data that you can actually take advantage of to find things and actually get information about that. And for very large cities, that actually can be something you can actually build a really interesting app from, or a really interesting even a business from, by just using city data. And as time goes on, the city data becomes more and more active, richer data sets, and also a lot more almost live data. Like I can show some. Chicago has some that gets updated like hourly, which is actually pretty nice. Which is good. And so I'm going to just demonstrate a sample location analysis that I came up with, just to highlight some of the things that we're using for this. Some of the things I mentioned and some of the tools we're going to use. It's contrived, but it's demonstratable. It can actually answer a question that you're curious about. Built using the low-level tools I mentioned. So shapefiles to well, actually, shapefiles in this case, I think I'm going to write data in shapefiles. I use use Shapely to do some processing. I'll use rtree to build a spatial index so I can combine two things. I use PyMap 3D to do a projection, and then I'll render some within a notebook in Python, but I'll actually render the final results with QGIS, just to kind of show you sort of like the pipeline for how that is going to run. So I'm going to start with this. And so what I'm going to do is I'm going to say, okay, what city of Chicago outdoor cafes are on busy streets? And why do I care? Well, I don't know. If I want to go to dinner or go out and I, don't want to hear a lot of traffic or breathe a lot of pollution when I'm sitting around, I'd like to kind of know where where the outdoor cafes are, and then sort of figure out where traffic is and try to figure out which ones are the ones I may want to avoid if I don't like sitting on sidewalks with traffic. As I said, kind of contrived example, but it actually can answer a pretty specific question that you might have, and you can go from there. There's lots of extensions you can build on top of this. So basic steps for almost any data science or any location intelligence is, do you have the data in order to do this? And so yes, if you have the data, you can actually start the project. I used to run a data science team, and we would come up with great questions, and then we realized we didn't have the data for it. So they sat in the dustbin, and eventually, if we had the data, we'd bring them back out. Otherwise, some are still sitting there. You need to load the data. When I say load data, you also kind of need to clean up the data, because it probably could be, not the most cleanest thing in the world. The data I'm going to use is point data, which is interesting, but the problem is I need to convert it into other geometries, because points are really hard to try to conflate together because they're infinitesimally small, and that makes life much, much more difficult. So I'm going to project these into what we call meterspace, and I can explain what I'm doing there. Process the geometry. So we're going to turn these points into something else, like a polygon that's more useful. We're going to take those polygons, build a spatial index. We're going to query the spatial index to get our answers of where the busiest streets are. We'll save the geometry shape files because we want to be able to visualize it, in addition to doing the results of this. And then finally, I'll show the final visualization. So the first step is getting data. Chicago's data portal is actually pretty impressive. It's the official data portal for the city of Chicago. It actually, in addition to data, has a bunch of APIs and other developer resources. People have made apps. The city of Chicago has made apps. The city of Chicago has had other people make apps for them, so you can do all sorts of different, build different services for the city of Chicago. As I said, they have a very large collection of data. They're also what was called an Open 311 city. Open 311 cities are really good about, so the standard is 911 if emergency, 311 if you're just going to complain about a pothole. So, you know, you want to log service complaints for city. They're tracked. There's kind of an open standard that various cities use. I think at this point, there's like 27 cities in the United States that use Open 311. It's growing, but the nice thing is they generate a lot of data artifacts as a result of that, and a lot of it is geospatial. And so City of Chicago, you can find data sets for all of what I just showed. So you can get, you know, the buildings, things about community, things about parks. You can find out a lot of things when it comes to public safety. Sort of food permit and health inspections are quite interesting. That's one data set that gets updated quite a lot. So if you want to find out if a place failed food inspection, you can easily find it. And, you know, all sorts of things, lots of transportation, a lot of service requests, where the nearest, you know, they have a list of the week's worth of pothole fills. So you can find out where the potholes were in the city. Kind of quite interesting. Somebody, oh, actually, that's fine because I'm going to go to my demo. Let me bring up the next one. So first of all, just to show City of Chicago data portal, you know, this is it. Lots and lots of, here's the food inspection, police station, street names, city loan, land inventory, which is great because you actually understand what the city owns. A lot of this is geospatial data. You can go and view it. They can map it if you want to. So I encourage you to look for the Chicago data portal if you want to browse and go through that. But in the interest of time, I'm going to go ahead and start with my demo. I use a notebook just because it'd be just easier to visualize some of the data in the intermediate steps. So I figured, why not? It saves me a little jumping back and forth. So I wrote a couple support classes to be able to do some of these things and some conversions, but, you know, I'm bringing in Shapely, I'm bringing in Pathlib. What else am I doing? That's it. So I want to use the lower level Python packages because although Geopandas can do it, the nice thing is that I feel you want to have a sort of a understanding of what's going on with this. So I figured I would go ahead and just bring these in. So I did two things. So first of all, I discovered that City of Chicago has a sidewalk cafe permits. So those are all the ones that all the restaurants that have needed replied for a permit to serve food on the sidewalk, and you get a giant list of what these are. I'm just looking at the top 10. You know, and so they have a permit number, account number, which is actually interesting because you can find out that there's like a lot of restaurants are owned by the same people. You get the legal name, you get what their actual true name is, so you know what they are. You don't get the LLC and all that. You get like the date it was issued, the date it expires, its address, a real weird breakdown of the address. And then the nice thing is that, you know, tells you what ward it's in, tells you what police district it's in, you get the latitude and longitude. So you actually do get its location, which is perfect because that's where we're after. So I'm going to load this into a data class. So I'll show you the one for the other data set that I'm going to pull in, but basically just wrote something that lets me create a small data class, loads the CSV, and actually dedupes it because this file, even though it's like 18,000 lines long, there's a lot of duplicates, so I've removed them, and it gets down to about 3,000 outdoor cafes, which interesting enough. So you can, in a notebook, you can, you know, quickly build a map of the city of Chicago. So this is it, just load it in. Basically just give it location, which is Chicago, latitude, longitude, what zoom level which is something about the geospatial organization I was talking about. So if you start at zoom level 1, or 0, depending on how you start, end up with the world, you go down to like 16, you're down to like a city block. So it's a way of organizing information, so you can actually not have to serve up as much information as you want. So basically, the only thing I'm going to do for the cafes is I'm going to turn this into a map. So I'm going to run and plot this, and let the map generate. I'm not going to run all these because it's already run. So now here's all my cafes that I have permits for, outdoor cafes in the city of Chicago. Typically, they obviously line up along streets, and you get a pretty good distribution of where they are. And you can see, like, Wicker Park has a ton. Division, of course, that they have giant wide sidewalks, so they have quite a lot there. So good observation of, at least that's my first step. Do I have the cafes I'm interested in? Of course. Got traffic data. So that's the next one I'm going to load. And so there's an average daily traffic count. So the city of Chicago did that a few years ago. So it's a little old. You could also find, you could mine data from other sources, but this is somewhat convenient one. Although, as I said, somewhat contrived, but we'll go through that. So we load it. We just take a look at what we have here. We have an ID. We have the address of where this is, what street it's on, when the count was done, which, as you see, was a while ago. So, but that is the one thing. Some of this data is kind of old, so you can do what you want to with it. But it does have latitude and longitude. Also, most important thing is it has the total number of vehicles passing through that point at any point in day. So, from 7,000 to, I think the highest number is over 1 million. I'm not sure where that is in the city, but I'd like to know that. So we're going to load traffic. We're going to process the traffic again, and we can load that. We can zoom in, and now, like, these, where the traffic information is these orange circles, in addition to the cafes that I just created. Okay, so got these two pieces of data set. That's cool. I've used Shapely to generate geometries. I've used Folium, which converts this to something that this map and can display on the map. I can do some other things, like nice thing is that this is actually kind of cool. So what I'm doing here is just getting the I'm asking for, of all the sets of data in both cafes I have, which, because I've loaded the latitude longitude, I'm just asking for turn that into a giant list of points, and that I get the centroids. The centroid is the average of where all these are. So now I know where the center of these cafes are. I'm going to use that number. I'm going to use that number to project this to what we call meter space. And why do we do that? Because one of the problems is that I want to do some calculations in meter space. It's very, very, very difficult to do that when you're talking about latitude and longitude, or degrees. And the reason why is that, well, interesting enough, Earth is obviously round. The way the degrees are is the lines of longitude that go north-south start to get closer together the farther you go north or south on the globe. So depending on where you are, a degree can actually cover a slightly different area. And so it's really, really hard to understand, to get accurate meter calculations using that. So there's a lot of libraries that will let you project this geometry. I'll show you the code on this one. I can get it in. Yeah, so there's two libraries. So I use the one that I mentioned before, which is PyMap 3D. Has a cute little has a function that basically says projects points to E and U, and E and U is what's called a local tangent plane. So you basically make the Earth around this one location flat. And so it's tangent to that point. And so I'm telling it that I want to give it the lat long, and of course I can do an altitude, but it's always going to be 0 because that's going to be the surface of where I am. I'm going to say, this is where I want to create this plane. And this is what I want to turn all my objects from latitude, longitude into degrees, meters. And so therefore I'm gonna break this apart. And so what I'm doing is it's called a geodetic because it's round. It's a space, and convert something into what we call an E and U, which, okay, it's a plane, and it's east, which is X axis, north, which is the Y axis, and up, which is the Z axis. There's also one called northeast down, which is if you're a plane is very convenient to convert to, or a moving object like a vehicle. So there are two different coordinate systems, and really one is just a 90 a flip of the other. So it works. I always remember, and you'll run in this whenever you do geospatial data, is that this function, I've modeled the latitude. Sorry, I do it longitude, latitude, because longitude technically is x-axis. If you look at the Earth, latitude is the y-axis, but because traditionally it was easy, everyone refers to as latitude, longitude. You end up getting these weird things where you sometimes have to do these flips, and this one unfortunately does latitude, longitude. So actually I have to flip these and make sure they're correct, otherwise my calculation will be off. Same with the result here. It gets, and with the center, because it's also in latitude, longitude, so you have to flip it. So basically all this does is that'll take this point and create me geometry, which call XY, which is a point, and then I'll go through and I'll get things back in my meter space. So I'll process this. What did it take? It took about 36 seconds to do this one. I did the traffic, it's 3,000 or 3,800 objects. This is about 1,300 objects, so it took about 12 seconds to do it. And then I have my cafes, and I have and my traffic circles turned into geometry. And what I want to do is I want to expand those out a tiny little bit, because I want to create what's called a bounding box, because these were points, and I want to turn these points into something that is actually not just a point geometry, but actually has some physical size in the world to be able to do some calculations with. So and then I'll project them I'll expand it out, project these now new polygons, which I'll show back into the my latitude, longitude, back into the real world coordinates, and then I want to actually be able to and I pre-calculated this, but this is what these points that we saw earlier have expanded out to. So now they're actually full squares, which gives me some coverage and some idea of some fuzziness around there, so I can use it. You'll see a lot of these tricks in geospatial data before. Same thing with the traffic, except what I'm doing here is I'm actually trying to make larger circles, and what I'm doing is some metric that says, give me the volume. Let me take a 100th of it. Let's peg it at 250 meters. Minimum size that I want is 10. So I can create these traffic circles, which roughly would account for, say, noise or pollution around a certain location caused by traffic. Now, very contrived, because really, the traffic is actually along these streets and not necessarily, we zoom in here, it's along the street, so it's actually more linear than it is circular, but it's not a bad representation for what I want to try to do. And so, plot this out, and that's great. And so the last thing I want to do, or the last two things I want to do, is create a spatial index. So now I have my traffic, these circles here, and I want to turn them into something that I can actually do queries against. And so what I do is I use in the traffic, I use Artree, which is one of the libraries I talked about, and I create a spatial index. And so really I'd make it a class, because I just want to keep the reference to the index. Don't necessarily have to, but decide to create an index. And then basically what I do is I take my traffic and I get my bounding box, which Shapely is very willing to give me for free, because any sort of object that's in Shapely will have a bounding box or a square around it, which is the maximum, the minimum box that will surround the entire geometry. And I insert this into a tree. And so what this does is it's sort of like it's what they call a spatial index. So it can actually do very, very fast lookups. The next thing I do is I want to take my cafes, which have some geometry, and I get their bounding box that I created earlier by making a 10-meter square. And then I actually ask for the intersection of that with everything within the tree. And that actually is super, super fast. As a result, I now have, and what I do when I'm doing that, sorry, the last thing I wanted to show, I forgot to mention, is I'm basically taking, I get back the list of all the intersecting traffic circles that I just created to this bounding box. And so I can get a list of these things. And so if there's one, I'll have an idea that, okay, this has some traffic near it. If there's more, then I really indicate that this not only is affected by the traffic, it's affected by a lot of traffic in the immediate vicinity of this particular cafe. And then I just basically add that as the number of traffic circles that are created if I query this into my cafes. And I get a list. And so here's my list. So I got the most traffic in the city of the ones that have the highest number of overlapping tracking circles. And then basically I just ask for the top 10. And so I get these, which are mostly on Dearborn Street or Lake Street. So in the loop. So not in and not surprising, but that's where they are. So, this has like 10 overlapping. This is 9, and that kind of makes sense because this part of the downtown has tons of these overlapping circles that I've created. So that's great. As I said, I did mention I save these out to shape files. So I'm going to give you a quick demo of QGIS. So, let's take a look. Here's all my cafes plotted on the city. Trying to make here's my traffic volumes, and so this is the traffic volumes. If you notice these are ellipsoids, it's because QGIS has a bad tendency to not render things because of the aspect ratio of this window exactly as round as it should. So it will it's a little distorting, but that's fine. When you print this out, it's actually not distorted. So that's great. I want to actually put this on a map so I can see where it is. And then the other one that you can do with QGIS is you can do some actually kind of interesting things where you can kind of blend all these circles together. So you get like this sort of heat map view of like the traffic information and where it overlaps cafes in the city. And so that gives you the ability to, produce some nice visualizations, and visualizations are great. They actually can give, for humans, can give you a really good insight into exactly where, things overlap. But in terms of actually, coming up with reports of where things are and numerical and quantitative analysis of what you do, you'd have to do what I did before, which is generate these sort of geospatial structures and do some location intelligence on it. And so, and then the last thing I have is just some examples of these images I created, which you just saw from QGIS, but this is sort of the results you can get. You can publish these. You can connect them with some other libraries, like I said, Mapbox and all that, render these out and actually have interactive maps where you can go through and find what the traffic density is for these things. So, yeah, that sort of concludes my talk. Back to Linda. Yeah, so that's great. And I see there's some questions. So yeah. Yeah, if you want to do a first project, this isn't a bad one, really. I mean, but if you just want to grab some data and plot it, my suggestion would be look up like I'm trying to think. Look up the Geopandas if you want to do it all in Python. If you just want to like start early, you could use Mapbox Studio. You can create. They charge you eventually if you start serving up huge amounts, like mere mortals probably. If you're just a hobbyist, you're not going to hit the thing. And you can start experimenting with the with this data. Pull some city data. QGIS is a great way to start because it's fairly easy to use. Like I can just pull in some of these different layers of stuff. And there's a bunch of other stuff you can do. If we have time really quick, I can just show you. Or maybe not. Oh no, I remember that this is starting to die on me, so I won't add more. But you can add, there's all sorts of data you can add into this. So yeah, it's a really good way to start. As I said, City of Chicago data is a good place to start. You can find things, you can, really anything is out there. Yes. Okay. So projections do. Good question. Very, very good question about projections. So there's a comment that all maps are lies because you have to make some sort of judgments and trade-offs between doing that. So yeah, there are some inaccuracies. So like this local tangent plane that I created, which has a center here, if I went really, really far out, if I decide to go out like to, I don't know, St. Charles or something, my accuracy would be way off, be off by a few meters, which is big enough not to do it. So a lot of times you will do you can do processing in these little cubes and then move along and march along. There'll be some slight inaccuracies, but they're usually not too bad. To be honest with you, like GPS, as good as it is not that great in certain areas. Trees and dense urban areas tend to throw off locations of GPS traces by like 30 meters. And there's even city surveys that actually have to do the surveys are probably the most accurate. And so you'll find inaccuracies in all maps somewhere. There's always some place that does it. So, but yeah, they will tend there is some always when you're converting from one coordinate system to the other, there's a little bit of inaccuracies that creep in, especially with the projections. There's not much you can do about it. The standard projection you see when you see the giant world map, and it's called the Mercator, is great because the idea was designed to preserve angles, but it definitely distorts shapes. And so, like Greenland looks as big as Africa on that map, and it's nowhere near that size. It's a 16th the size of Africa, but it just because of the way it gets distorted as you get close to the poles, it causes inaccuracies. So there's all types of distortions as a result of that.
All right, Craig. I think that's the last of our questions.
Cool.
Unless anybody's got any more. I haven't seen any show up yet. So with that, I think I'll conclude this meeting at ChiPy.
you.
Craig, thank you for speaking.
Thank you.